Hi, and welcome to this short concept bite. When describing different types of thermodynamic system, I have already introduced you to the terms heat and work, but both of these terms have very specific meanings in thermodynamics. This video will cover the term work, or more specifically, expansion work. In a thermodynamic sense, work is a mode of transfer of energy that achieves a uniform motion in the surroundings. There are many types of work, from raising a mass to powering a computer, but regardless of the type of work, the amount of work a system can do is independent of the type. Consequently, we usually model work in a thermodynamic sense with expansion work, the work of a gas expanding against an external pressure. This breaks down into two different examples, which will be described in this video: reversible and irreversible expansion. If we consider a gas in a syringe or piston with an external atmosphere exerting its atmospheric pressure on the piston, then if the pressure inside the syringe is higher than atmospheric pressure, the piston moves out. And it will continue to do so until the pressure externally and internally are the same. As the piston moves, the system is doing work on the surroundings. If we look at this on a microscopic level, looking at the atoms on the piston's edge, those atoms are showing a uniform motion outwards as the gas in the system expands. Mathematically, this expression has a constant external pressure, and we would call this an irreversible expansion. The work done is the change in volume multiplied by the external pressure, and this area is shown on the graph. Now to consider the case of reversible expansion. Thinking back to what you have learned about ideal gases, you hopefully remember the relationship between pressure and volume is given by the ideal gas equation, PV equals nRT. At constant number of moles and constant temperature, there is a reciprocal relationship between pressure and volume, as shown here. Work done in an expansion is the pressure times the change in volume. If we consider the pressure changing constantly, we can see that this would have a relationship to the area underneath this PV curve. The work done, or area, is more than seen in the previous example. In fact, the work done in a reversible expansion is the maximum possible amount of work that can be derived from the system. This can be generalised further to say in any thermodynamically reversible system, the work the system can do is the maximum possible amount of work for that system. A truly reversible expansion is an entirely hypothetical case, as it would need the system to be in mechanical equilibrium during the whole expansion, and therefore the pressure inside and outside the piston would always have to be the same, and we are changing the pressure of the surroundings, or rather, the expansion to occur, the pressure inside the piston is only ever infinitesimally higher than that outside. This reversible process is shown on the left, with the work highlighted as the area underneath the curve. The irreversible process is shown on the right. Here the external pressure remains constant as the gas expands until it has the same pressure as the surroundings. Since P here is constant, we can see the area under the curve is smaller, and so less work has been done. The equation we used earlier, W work done is equal to Px delta V, gives us this area. How do we determine the work done during a reversible process, or the maximum possible work a system can do in an expansion? I'm going to start by the result. The area under the plot is given by the work done is minus nRT log Vf over Vi. If we start with the relationships for work done, shown earlier, and the ideal gas equation, the top two equations here, you'll notice I've arranged the ideal gas equation to make P the subject. This is because I want to be able to determine the area under the curve, and I'm going to do this by integrating the volume, the x variable. Replacing P in my work expression and integrating with respect to volume, adding up lots of infinitesimally small changes between my initial and final volume gives me the expression from the previous slide. This is a very quick derivation to the work done in a reversible expansion, and I encourage you to sit down and work through this in your own time. In a reversible expansion, it is not that the system cannot return to its previous state. It is just that we cannot derive the maximum possible energy as work from the process. I hope that this short video has been useful in explaining to you the concept of thermodynamic work and the difference between reversible and irreversible work. As I said, I highly encourage you to look through the math derivation in your own time. If you have any questions, please do not hesitate to contact me.